So promised last time, today we are going to discuss functions, relations, and so we'll start with set theory as we will be using the concept of set theory in calculus. So set theory. What we see necessity of set theory. As usual, the father of physics, and we can call him Galileo, he came up with a paradox. What was that? He said there are squares which are square itself is an integer. Square is an integer. So when you look at to the order, let's say square is an integer and which is square of an integer. Okay. Let's say if you take square, for example, let's say take 4. 4 is a square of what? Square of minus 2 plus 2. Right? So square 4 is an integer, 2 is an integer. First 2 later. So he said, since there are fewer squares, there are more integers. So this set must have been greater than the size of the set must have been greater than this. So he said what he concluded paradoxically is that the concept, or you can say comparison, operators like greater than, smaller than, or equal to, these operators can be applied only to finite finite sets. For infinite sets, there is no, you cannot do. But in 1884, a gentleman by the name of George Cantor, he came up with the concept of uh, set. He said, though the the total integers, set of total integers is greater than the set of squares, you can compare these by making different sets. Let's say here we have set integers I. In I, you have the set numbers in the integers of real number integers. Here you can have another set which is squares. Yes, this square will contain only 1, 4, 9, 16, 25, like that. So you can compare these, whether this is less than greater than this, whether this is less than or equal to this. You can make two sets and then you compare them differently. So that's how the concept of sets came into being, and it was very useful in interpreting a lot of mathematical, physical concepts. In fact, based on set theory reasons, that was the paradigm. So the reason behind this set theory, invention of set theory, in a way, in a way, there are so many geniuses who worked on these things that Galileo was, as usual, the father of physics. He came up with this paradox, which is not very good, doesn't reflect very well on him, his capabilities, because he thought it was where the operations can be performed only on finite sets. Anyway, now, so that's how the set theory will first started. And set, when you define set, what is a set? Set is, as I told you, any collection of objects. It can be males, it can be female, set can be females, it can be children, any set of objects. Right? A set of objects is, you can call it, what we call set, a set. And uh, then came, of course, George Cantor came up with this. And the basic definition of this is, if there is an element, you want to define the set, then the set will be represented like, if A is a set, A is equal to, we use flower brackets, X, such, we call this such that X belongs to R. So this set defines all the numbers of the negative, positive, all real numbers, real numbers. Ordinary R, you should differentiate between ordinary R, simple R, and this bar over R. This is real set of real numbers. This is generally represents solution. So you should go with it. So this X A is set of all integers, I mean elements X, that X such that X belongs to R. This is belongs to. There are certain mathematical symbols that you should know. Of course, since you are here watching a mathematical program, you must have good knowledge of mathematical symbols. But and yeah, there is, uh, when we come to sets, there is a, what do you call, representation, how we represent sets. It's called Venn diagram. Venn diagram. This Venn diagram is like it is like a circle. So another set. This is one set A. This is another set B. This is another set C. Let's say. So this A contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11, 12, let's say. So you can represent sets with well lines, nothing but circles. And let us see what are these different shapes denote. This shape here is called an intersection. So A intersection B, A intersection B, what will it be? 4 and 5. So it is the convention of the elements. 1, 4, 5. This we can set A intersection B is 4. Here, let's say B intersection C will be B is all these numbers and C is all these numbers. So that will naturally contain B is starting from 4, 5, 4, 5, 7, 8, 9. Yeah, these are they belong to B intersection C. That will fit this portion. Then there is another C intersection A equal to C intersection A will be, oh, sorry, no, so I'm just thinking of union. So this is B intersection C will be B and C intersection will be B is this one, C is this one. So only 5 and 9, 5 and 9, 5 and 9 will be intersection. So now C intersection A, this is C, this whole thing is C, and this whole thing is A, meaning these two intersect at 5 and 6 alone. 6. Let us now write down A union B. Let us see what A union B will be. 1, 2, 3, 4, 5, 6, 7, 8, 9. All the elements included between this values, those will be A union B. Similarly, we need not go for everything, B union C, C union A, all that. And let us go straight away to uh, A union B union C. What will be this? This will be A union B union C is all the elements, in fact, all the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All elements will come to A union C. Right? You can perform multiple operations on A union B intersection C, A union A intersection B intersection C intersection. Like that will be an interesting one because A intersection B intersection C will be very limited because it should be intersection of all the three. Which is the intersection of all the three? Only 5. Yeah, only 5 is intersection. In is 5 is in all 6. Right? let's say it is 4, 4 is in A and B, but not in C. 6 is A and C, but not B. 9 is in B and C, but not in A. So only 5 will be uh, intersection, A intersection B. That is how we define the Venn diagrams, and this is the set builder notation. We call it set builder notation. Now, let us go further. Let us go to the concept of subset. Subset, as I told you, this is the whole population. Population of world. There is a set containing only nodes. But there is a set containing nodes. These two are actually, let us say this is whole, which is male, which is female, then M and F are subsets of the population, right? People. Meaning these are included in this equation. This is called superset. These are called subsets. Right? And there is one important um, law, that is every set is a subset of itself. And there is one more rule which says empty set is subset of all sets. So if you take three elements here, let's say uh, X, Y, Z, here you have X, Y, Y, Z, ZX. Here you have only X, Y, I mean X, Y, Z. That's it. If you take three, then these two, the, and this. How many? There are six. Six are subsets of this set, superset. And the rule is, if there are n elements in the set, a set contains n elements, then implies that there are how many elements? U raised to n. Here we have three, meaning this should have been just n is three here. The elements should have been how much? Two. The rule says 2 to raised to n. But how many we have? We have 1, 2, 3, 4, 5, 6 only. Why? Because apart from this, always there is an empty set, which is represented as um, um, this that is like an empty set. Basically, this empty set now for now. Later, when dealing with functions, we will know what empty set is. So this is empty set, and there is of course the set itself. This set itself, let's say, yes, this S is a subset of itself. So how many we have? We have 2 raised to n, 2 raised to 3, that is 8. We have these many subsets. Now, how do we represent a subset? A subset, we represent a subset as if A equal to x, y, z, B equal to x, y, then B is subset of A. This set contains only xy. This contains, apart from xy, z also. That's why this is going to be subset. Or sometimes, let's say in B we have the one, let's say, in we have x, y, z itself. Then what will it be? A is subset of or equal to B. So B is subset because we are following B condition. B is subset of or subset or equal to A. So when we say the every set is a subset of itself, we can say that A is subset of A. That is what sense. Because here this word itself is considered every set is a subset of itself. So A is subset of A itself. That's one. Um, but we had, let's say, A equals B, B equals B, then B is called a proper subset. Okay. So why it is a proper subset? Because a subset is actually by intuition, when you say subset, it should be included in the superset. This is the superset, this is the subset, and this proper subset, any subset, should have been included in the superset, not superset. So the condition is we should always have less elements, less objects, uh, less objects than A. Only then we is a proper subset of A. There is one more concept called set difference. You can say just like union intersection, you have set difference which is limited. So nowadays you not thought about this. Union, this is like this. The across the A. That means we set up all the members that are not in the set. So you can say there is U, a set U, 1, 2, 3, 4. There is set A, that should be proper prediction, could be set A. You know why I have an intersection. This is 1, 2, 3, 4, 5, 6, 7. So, then whatever objects that are not there in U, that are in A, this is not what do you call intersection. Intersection, what is intersection? U intersection A will be this portion, right? Only 5. But U minus A or U difference A will have, what will it have? Whatever are not there in U that are there in A, but those are 6. This is difference of U and A. There is another. Uh, Please bear with me. I will be getting the code very often because I like it very small. So I will be getting it with me. Open. Now there is a symmetric difference of symmetric difference means it the symmetric difference is like, let's say in A we have 1, 2, 3. In B we have 4, 5, 6. So not bad. Let's say 1, 2, 3, 4, 4, 5, 6, 7. This symbol is very weird here. They a triangle symbol that is symmetric difference. Or it can also be represented like uh, this. Okay. So what in a sense what it means is they could be in both. Um, they could be they could be differently with different objects here, different objects here, but they should not be in both. Huh? Insects. One of the section, let's say it is 1, 2, 3, 4. This 4 is the culprit here. That should not be in both. So it could be here, it could be here, but it should not be. That should not be any object should not be common to both. That is called the symmetric difference. And above all, we are coming to the last one. Yeah, let's say we have x, y, z, t, 1, 2, 3. Yeah. Then we have the Cartesian product of A and B. A, which is represented by multiplication symbol. A was to meaning this is basically called the Cartesian product. This will basically all the ordered pairs 1, 2, x to x2, y2, y2, z2, z2, z23, z24, T2, T22, T23, T24. All ordered pairs this Cartesian product. All possible ordered pairs. These are pairs. X2, y2. Those are called the pairs. Those ordered pairs. All total of those ordered pairs is called Cartesian. And and of course, the last one, let us say here for about sets, the power set. Power set is what is power set? Power set contains all the, including empty, contains all the combinations is uh, possible subsets. Power set, let us say, if you have x, y, z here, a, x, empty set, a, x, y, z. It contains all the subsets. The subsets in sense of just these are objects, and the subsets could be the xy could be one subset, xyz could be one subset, yz can be one subset, zx can be one subset, something like that. So uh, I think, yeah, basically all it is the set of all subsets. Okay, empty set. So then we here because this is not subset. We have not subset here. Let us take another. We were talking about only this, but we are taking the set of 1 is 1, 2. Then the power set will be the empty set. Yeah, those were not actually objects. These are subsets themselves. So let's say even here, if you have x, these are subsets. While yeah, this is the set A. That's power set. A will be empty set X Y. That will be the it will be a bit confusing. The thing is, once we go to functions relations, everything will be clear because one of the main uses of set theory is using them in functions, functions relations. Okay? So now we will come to functions. Then we come to talk of functions. This is in fact the brain of modern, all modern technologies. Um, Now, why I talked about set theory is because in functions we will be making use of set theory and set notation. Function is the one which which maps an element of a set X, let's say, to an element of its set Y. Is denoted as function X maps X to Y. This is a set. This is a set. Y is a set. So this function maps. This is X. This is Y. 1, 2, 3, 4, A, B, C, D. Then this maps each element of this to an element of this. Okay. Every element of this to the element of this. But there are types of functions which are bijective, injective, and surjective. What are these? These you can in another way say bijective is one-to-one distinct ones, one to distinct one. Injective is you can have all the uh, elements of this or mapped to this. Um, Even this could be one to one here, but in such you will know the difference why it is so. Uh, Subjective in subjective, let us see. Let us go to one up to 1, 2, 3, 4, 5, A, B, C, D. Let's see. So in injective, um, yeah, in the injective, we have these mappings. There you can have elements which are not mapped, which is not mapped to either of them. Injective, okay. In subjective, one, two, three, four, three, one is mapped to the other is mapped to the other is mapped to this, the other is mapped to this. So, in subjective, more than one can be mapped to one element. Yeah, more than one dimension X can be mapped to element of Y. So that can be, this is subjective. So, bijective is both injective and subjective. Meaning, this subjective can one X can be mapped in the element. X can be mapped to more than nothing. One, sorry, more than one, more than one. Elements of X can be mapped to one element. Yeah, that is so. So bijective is combination of these two, which makes it uh, both injective as well as subjective. Right? So those are the three kinds of functions that we have, and actually, this is not how we will reach functions to begin with. So how do we know the functions? Functions are like input x. Here, this is a function which converts input to output. So the other term for other, there are many terms. You can call x element of x. X is called variable. It is called, okay, X is when we map from functions, X is called domain, Y is called codomain. Um, element of X is you can call it variable, uh, value of variable, value of variable. Here you call this um, value of function here. This is the value of function as the map or image. And when you take all this, let's say when you're mapping X to Y, let us say you have um, X to Y when you are mapping all the elements that belongs to let's see, X. A belongs to X. Um, for every let's say A belongs to X, B belongs to Y, let's say this pair which we have mapped from here to here. Let's say 1 to let us go this one. Let's go A. So 1A is a ordered pair. We call that the ordered pair. Okay, and yeah, let's to midway, I think, and going back to because we came from set theory, we tend to let many things based on set theory. Now, this ordered was, yeah, we said function is one which maps mm, the elements of this to um, set x to elements of set 1. This we call one, let's say, one A, 2B, 3C, 2B, and 4C. These are called particles. And this can be represented as y equal to fx function. This set y, the elements of set y are functions of x. Then in other way, we can either represent this f function f maps x to y. That's what we can do. Sorry, this function has a value. Let us say this has a value fx is equal to x squared. Meaning, this is the value of variable, this is the value of function. Given this input, it outputs this value. This is value of function, this is value of variable. So, yeah. And the function need not be as simple as that. X could be 2x plus 2, let's say. Then f of 1, value of x is 1, so for value of x equal to 1, 2 into 1 is 2 is 2. Uh, in such case, you don't have direct value of function here. Here you have if it f for f of 2, let's say x squared is 4, you have directly you got the value of function here. But here in certain functions, you may not directly have like this. You may have to evaluate. This is evaluate function to know value. But that is one way. And the other way to represent the same function would be, let's say, x maps to x cube. That is, here we are not using f of x functions. We are using directly using the function itself, the input value and the output value. So this representation is also it snaps. You can directly call this. Let's say it's cube. We all know this cube. Right? You can directly call this cube. These are all just different ways of calling a function, different ways to represent a function. So yeah, not the most popular way of representing function is y equal to y is basically yeah, this is also called graph. Let's say x belongs to R. Graph. Yeah, okay. Real value, real functions, we have reals, we call them, they belong to the subset of real. So in real integers, if you represent a function, let us say, just now say we learned that it can be called graph of function. So when it is the condition both uh, x and y should be real integers, real, to belong to the real numbers. So if you take this x-axis, you take this y-axis, and you have a graph, let us say, something like this. Then, then this can be when these both are real, belong to x-axis. These values and these values both belong to real, set of real numbers. Belong to set of real numbers. Evidence from the finger. No, it will not compose it. It will not belong to compose it. It will be to C. Right? So let us say they will belong to x equal to belong to real numbers. Then you can as well call this Cartesian matrix. And this about yeah the representations of how we can represent a full function and a partial function. Full function, let us say, then a full function with this value x here is called full. definition of domain. When this definition of, let us say it is not sin x, there is some other function which starts here and ends here, let's say some curve, then this portion of real number, set of real number, is not included here. This portion is not included here. Right? So then we say from here to here only, this is the definition. Whereas this whole minus infinity to plus infinity, that is whole dimension, whole domain. That the whole domain is this one, and this one has only part of it, then that is called the definition of domain. And if the definition of domain, let us say D, or D, is subset of X, then you call this a partial function. Otherwise, if D is, no, no, sorry, this equals to D is subset of X only. If D is subset or equal to X, then it is a function, full function, right? Because this D can take values minus infinity to plus infinity. I mean, not minus infinity to plus infinity, but we are just doing the whole thing, real numbers domain. It's not so. X will be defined with this thing. So if this D, whatever it is, D, so, this one, this is using only, let us say, for example, only these two, these three, it is not using this one. Meaning, then it will be the subset of the domain. So then it is not a full function. But whichever is using all of them, only then it would be full function. That is the full function part, partial functions. I'm not going to into the because anyway we have to cover it when we discuss the symmetries, groups, and later. So then we will discuss it. So okay. Let's see, probably we'll call it today, but today we will call it. And we will cover relations, relation uh, next in the next. Okay. Thanks for watching the video. Uh, we'll meet next week. So discuss videos.